There we are. Okay, so class agenda today. We'll start with assignment 3. I realize I was super delayed in getting these out, so this will be weird, but it'll be due after the class is like technically over. So we'll end on Wednesday, but then when we look at assignment 3 and like final model object submission, those won't be due until next Monday. And then we'll push the course back a week because I'm going to be out of town that week anyways. So for our next, if you're in the next class following this one, if you're in the model evaluation metrics, that'll start on the 18th. And then it'll go 4 weeks after that. Maybe I'll send out a summary of all those dates. It's kind of hard to speak on the fly there. So assignment 3 and final model object submission a week from today. So I believe that's the 11th. So I have those 2 documents out there. We'll go through those. And then at the end of the class today, I'll have you guys and I will walk through all together, all of us, and create a topic sheet for Wednesday's exam. So right now, just a blank sheet, intro to ML exam. It'll be approximately 1 hour, about 1 hour, and we'll have like 20 to 25 questions. So we'll just all go through this and we'll add some topics and use your knowledge of the people in the spirit of ensembles today, which we're going to talk about in part 3 to study for that test. I get studies a strong word. You guys don't need to like cram topics. This is just a validation thing, and it's more for me than you guys to help me know this is where like I can improve in terms of communicating, and we're just going to talk about core kind of concepts in here, nothing too like crazy nitty gritty. Everything I would expect that you would know by the end of like a machine learning course. Okay, so classification and logistic regression is what we're going to touch on for the first part of today. We do a really fast classification review, and then we're going to talk about logistic regression, which is a really, really foundational machine learning algorithm to data science. And it's basically the partner to regression, but on the classification instead of the, the partner to linear regression, but on the classification side instead of the regression side. So we'll figure out why the word regression is in logistic regression here in a minute. And then we're going to talk about non-parametric models today, and specifically we're going to talk about a decision tree. And this is probably the most difficult assignment that I have, I think. Actually, the reason it took me so long to get the assignment out is because I always do all these myself too. And what I had originally written was for you guys to code like an entire decision tree by hand. After the 3rd to the 4th hour of trying to do that myself, I thought this is way too much. So not quite as much as I had anticipated. So I tried to make some preformed functions here. And then you're just implementing one element of the decision tree, which we'll talk about here in a second. So that's why it took me so long, because I realized that was way too much. And so we're going to talk about decision trees, very, very important algorithm in data science, in that it's a foundation for many, many other models. So if you understand decision trees, you need that to understand random forest, which is probably, if you look at the most popular models used on Kaggle, which is that website of competitions, you're going to see 2 distinctive models. One, you're going to see neural networks, which are very, very good, but you're also going to see random forest and gradient boosted trees. So 2 of the most popular algorithms in data science, because they're very, very fast to train. Neural networks sometimes can take a lot of iterations to really get the structure and the form right. Random forest, GBT, really easy to understand, really fast to apply, and like such a great like thumb in the air baseline model. I always train a random forest first as like a baseline model. So decision trees are critical to that. In interviews, one thing an interviewer will typically ask, and I ask in my interviews, is can you pick an algorithm of your choice and walk me through the steps of it, like describe the algorithm. I always pick random forest, so I'm going to try to convince you guys that that's a good algorithm to pick today, because it's I think it's more intuitive to explain than like linear regression, verbally at least. So we're going to talk about that, and then we'll spend the last maybe 20, 30 minutes talking about the sheet. Okay, so let's look at this class schedule because I messed this up again. We have gone through all of these sections so far, so 1 through 5. And then today we're going to talk about classification, trees, and ensembles. And then I'm going to post after probably Thursday or later or throughout the course. I'll tell you when I post on unsupervised learning, deep learning, and NLP. And I think the thing that I was struggling with was finding 3 hours to actually do this. So I'm going to break this probably down into one. It'll be easier for me with a 1-year-old at home. If I break these down into like 1 hour, knock that out before he wakes up in the morning. So that's probably what I'll do with those. So 3 1-hour segments. Then we'll have, exam is such a strong word. We'll have like the course exam test, I guess, a couple of questions you guys can answer for March 6th, and that'll be at the end of class. And then during that class, we'll talk about probably serving models to production, some like ethical considerations, some parting thoughts, but none of those will obviously be on the exam. So what the exam will corely cover is really just these topics here. I mean, maybe a little bit of data wrangling. I have to think about that. Got to go back and look at what's in there, but potentially that, but really just mostly linear regression, modeling methodology, classifications, trees, ensembles. So that's going to be the core content of that. All right.
Chat says that he's on, but I don't see him on the actual StreamYard, just so you know.
Oh, there we go. Thank you. I have to add to stage. All right, that's the agenda for today. I've wasted enough time, so let's dive into assignment 3. This is assignment 3, so this, in kind of summary, or my hope of this course is that you're able to just pick up a data set and train a grid search over it, tune a model over a data set. And so that is the whole part of part 1. I think we've done a lot of this already. I think you can go find code, or if you have questions, I can point you to code too. Select any data set that we've worked on from this class. If you really want to use one from outside the class, that's fine too. I think it's going to be easier if it was one from within the class. And then just apply a grid search. So you could select the iris data set, for example. Go copy paste all the steps you did for that, and then just add a grid search at the end of that. Then I just want to know what parameters you trained over and what were your best parameters selected. That's my goal for you to realize how to get the best parameters selected out of that model. So that's the key piece there. And I have examples of all of that. So that one it's maybe going to be a little bit of code because you're going to have to go through all your steps, reading in your data, fitting your model, doing the grid search, getting your final model, and then pulling out those parameters. But I labeled that as 30 points because I think this part is going to be maybe a little difficult. So I'm just describing like our decision tree algorithm here and maybe trying to explain some steps if it's helpful. What I'm going to have you do is implement this Gini impurity, which is what we're going to learn today. So I just made a fake data set here. Some X values and then some Y values. They're all binary, all 0, 1. And so I really, really oversimplified this decision tree. And I have a couple of methods here. One's called calculate Gini impurity. And this is Gini impurity. It's 1 minus the probability of class 1 squared minus the probability of class 2 squared. And so you're going to implement that in the code here using this X column and this Y target. And you can change any of this code as you want. This is just kind of how I wrote it, probably poorly. So I wrote this code that determines the best split, and it calls that Gini impurity function. So you call this best split, determine best split, you pass your X and Y, and maybe after we go through decision trees, I'll go through this a little more. but basically it'll pass each column and the Y target to this calculate Gini impurity, and you need to delete this random function and like maybe put in a couple of lines of code in here that'll calculate Gini impurity. You can also, this is also very widely searchable on the internet, and I would encourage you to look that up. So then the question is, this data set is just all zeros and ones, and at the moment our data set just contains features with just the value 0 or 1. It has this feature, or it doesn't. Theoretically, how might this algorithm extend to a column with 3 distinct values? So 0, 1, 2. So I tried to make this kind of the simplest form of a decision tree possible. And we're just determining the split at the first level. So maybe we'll come back to this after we talk about decision trees. It's a little weird to talk about it now. We haven't even figured out what those are. Okay, and then the last piece is just the final model object submission. So this is kind of like our final project for the course, except I'm not going to have you do a write-up or anything so formal as that. So just train a model over this fraud detection data set. I believe we shared this last time. Just use the train CSV, don't use the test. We'll evaluate over the test set, and there's no plus or minus points for performance across the test set. So it's just for your own personal interest. But what you will hand in is a joblib file. So I called this one my awesome model.joblib. You can call it whatever you'd like. You will run this code that will say dump. It's like kind of like an export function, and then you'll pass it your model, your actual model. I called it best estimator. And then I believe, you're going to want to validate that this runs, and you'll just call load, and then you'll pass in that file, and it should be in the same directory. You're just going to validate that loads in. That way I don't have to run all of your notebooks to create each and every file. You're just handing me 2 things. One, this notebook, and then the second thing is your joblib object, or pickle if you choose to use pickle, but I just put joblib here because I thought it was simple. So you'll hand me this object, whatever this, it's sort of like a zip file for a trained model type of thing. And then you'll hand me also this code, just in case I have any issues reading that in, I can run your code to do that. Okay. Happy to field more questions on that as you guys sit on that.
You said that the data set for that final model object was already used before? I don't think we used it. I think I brought it up last time, but I don't believe we have used this. So you'll have to download this training data set, and it's a fraud data set where you're trying to predict fraud. So the target variable is where's our target index? Oh, I just didn't scroll down far enough. Is fraud. So that's what you're trying to predict here. Oh, this doesn't scroll over because it's too big, but at the end of this, there should be a is fraud flag, 0 or 1. I think in the breakouts, we're going to try to apply logistic regression to that. So maybe that can be some time we spend on downloading that and getting that all set up. Okay, let me see. Just as a review, when we'd been talking, or we'd previously talked a lot about
linear regression, where we were trying to predict like a scalar numerical value, like house prices, where it wasn't a category, it was something that existed on a range of values. And the question arises with a data set like this, where when x is 0, y is 0, when x is 1, y is 0, when x is 2, y is 0, all the way up to 4, and then when x is 5, y is 1. So you can see those plotted over here. We have on our y-axis, y is equal to 0 when the input is 0, when the input is 1, when the input is 2, when the input is 3, 4, and then it jumps way up here. And it's 1 when it's equal to these values. So the question is, could we model this with linear regression? And yes, we probably could. But would it really make sense to model this with linear regression? Because linear regression could put out a bunch of outputs. It could put out a predicted probability of 2, or it could put out a prediction of 7 or -5. And so should we maybe strive to choose an algorithm that's a little closer to this domain, that maybe bounds between 0 and 1? So we have binary classification, and that's binary classification is when you only have 2 labels, 0 or 1. It is something or it isn't something, or it's this thing or the other thing. It can't be anything else. So it's fraud or it's not fraud, for example. And we're going to come back to this picture. But I guess another one is spam classification. So you have emails, they're either spam or they are not spam, and you have to choose how you put emails into that box. You have fraudulent transactions, perhaps speaker identification, you use sound waves as input. Is there a cat in this picture? Is there not a cat in this picture? So there is something called the logistic function, and that's where logistic regression gets its name. And it comes from this form of the sigmoid function. So there's this curve. This is what the sigmoid function plotted on a graph looks like. There's this curve that represents as x goes to -infinity, it always approaches 0. And as x goes to positive infinity, it always approaches 1. And this is the formula for that. It's 1 over 1 plus e to the -z. And there's this guy that did a bunch of stuff on population genetics, and that's where this kind of curve came from. You have kind of this lower population, and then they're growing, and then at some point the population stagnates. It's used a lot in population genetics. But the input of ranges for x can be anywhere from -1000, it's still going to predict 0, all the way up to like +1000, it's still going to predict 1. So -infinity to +infinity. But the outputs for y are always bounded between 0 and 1. So the inputs go from negative to positive, but the outputs, it bounds the outputs to this probability between 0 to here in the middle, this is 0.5, and all the way up here is 1. So all the values that fall between 0 and 1, that's our output for y. So essentially, the logistic function scales a range of numbers, of x input numbers, to a range of probabilities, because everything between 0 and 1, that's how we get our deciles, 0.1, 0.2, 0.9 probability. So if we look at this binary classification problem, where we had this x data set, which were numbers that ranged from 0 to 9, and they each had a y value associated with them, either 0 or 1, we can apply a sigmoid function here, and suddenly we have a way of mapping these input values to probabilities. So we can say, for example, this one over here, an input value of 4, x as 4, we can come up to this sigmoid function, and say that, oh, that's approximately a 0.4 probability. And that's how we get the probability output from a logistic regression function. So each of these map, just like we did in linear regression, we found where the X inputs met the line, and that was the prediction. We're doing the same thing here, but in this case, instead of it being kind of a straight line, XY axis, we have this sigmoid function, and then on this y-axis is our output of probabilities. I'm not going to go through the functional formula here, but there is one interesting thing that I do want to know, which maybe I'll rewrite it on the whiteboard because it's going to be hard to describe here, but yeah. That is the form on that slide is not the way that we've been talking about it. That's more of a linear algebra. So we're gonna do it. I don't know how to make this thing stay. I'm not very good about that. Let's just. Okay. So I'll rewrite it this way. In linear regression, we talked about, a good thing for the test. We talked about y, I guess we can call it y hat for this, and I'll make it lowercase, sorry. Y hat equals mx plus b. So that was kind of where we started. And then we said, well, we can write it a different way. We can write it y hat equals beta sub naught plus, I guess I'll put the sub naught, beta sub 1 x, right? Where in that formula, all we did is we moved the b to the front of the formula instead, and we made the m a b. We made the m b sub 1. So we put this b over here and we called it beta sub naught, and we made that an m, we made it a beta sub 1 instead. Where, in this, what these are, beta sub naught is our intercept. So if we have this graph and we have y equals mx plus b, and that's 0, 1, 2. In this graph, our intercept is 1. Your intercept is when all other betas are equal to 0. In maybe kind of like human language, it's when all of our other columns are equal to 0. When all other calls equal 0. So if we have like this this housing data set, or I'll do housing. If we have our housing data set and we're trying to predict the price of the house, our y hat price, and we have some numbers here. Our beta sub 1, beta sub 2, beta sub n, those are our column names. So maybe beta sub 1 is like number of bedrooms. Well, when all these are 0, when all those are 0, you get your intercept. That's where you get your beta sub 0. Okay, that's just review. So beta sub 1 is going to be your column. So if we didn't have any of these other columns, we just had price in one column, that would be beta sub x. So we took these foundations and we built on that. And we said, well, we can extend this. What if we have a lot of columns, like our housing data set, and they go beta sub n? We can say beta sub 0 plus beta sub 1 x plus beta sub 2x, and then we can do dot, dot, dot plus beta sub n x. So that's just saying that all the way until the number of columns that you have, you'll have all these little little beta things. Okay, so that is the formula for linear regression. This is my sloppy way of writing that formula. There we are. So that's a formula for linear regression. So that's where we started. The interesting thing about logistic regression is, like I said, this is, first of all, I should say this is for regression problems. And this is for classification problems. And the output for this one can be negative infinity to positive infinity. The output for this one is between 0 and 1. So when we look at logistic regression, clarity there we go. So when we look at logistic regression, it's this formula, this y hat is equal to 1 over 1 plus e to the negative, and this is where it gets interesting. What you put in this actual parentheses up here, and I'm going to put in here, is actually the linear regression formula. So that's why I'm rewriting it here. So it's this beta sub naught plus beta sub 1 x plus beta sub 2 x all the way to beta sub n x. There we are. Sorry. Got really long here. So that is, that was my whole point. I guess that's what I think is interesting about logistic regression, is that it is the linear regression formula that we learned. It's just scaled to the probability between 0 and 1. So it's that exact formula, and then there's this mathematical equation called a sigmoid function, which a sigmoid function, by the way, just for comparison, I know we had it on a few slides ago, but is equal to 1 over 1 plus e to the negative, what did they use, k? Maybe negative k, something to that effect. But anyways, what we put in for k is this linear regression function. So that was very interesting to me when I found that out. So it just scales the linear regression function on that sigmoid, that S curve. Sometimes you'll hear it called from 0 to 1. So that is why the word regression is in here, because it's logistic function applied to the linear regression equation. So it gets a little confusing because it is used for classification problems, not regression ones. So it's a weird term for that. But all right, that's like the heart of logistic regression. Let me see what else. We'll switch back to slides here. And I'll take a picture and drop that in the chat for everybody on
the bottom.
Yeah.
Sigmoid?
Sigmoid, sorry. S-I-G-M-O-I-D.
Okay.
All my letters are squished together. Okay. I think that's all I was going to say. Yep, apply sigmoid to linear regression. Oh, no, I did that right. Good. I thought I forgot the negative for a second. I didn't. Good. Okay. There's some interesting stuff in here. You don't need to know this, but the B, what I have in my formula as the beta sub naught, beta sub 0, is the midpoint. So when we look at this graph here, this midpoint here, that 50% probability, 0.5, changes with B. So you can shift this so that instead of having B at 0, you can have it at -6. So You don't need to know that, but it's interesting. And then the steepness is determined by the combination of those parameters. So right now we have kind of like a really gradual curve here. We could really stretch that out so it took a very long time to get over there, or we could make it like happen super quick. So right now you can kind of see between maybe -4 and +4. You kind of make most of the way between these, but maybe we wanted that to be between -2 and +2, and it just, that steepness happened really fast. So that's kind of how those things change.
Why would you want to change the midpoint? Like you said, B, it alters when you, I guess, when you consider B.
Like a 50% probability. So maybe for your problem, for your data that's going into it, it isn't centered about 0. I'm trying to think of an example. Man, I remember just a couple of days I thought that would be really useful for X, and then I can't think of it now. Maybe it'll come to me. Maybe it's in these slides that spurred it. Oh, it might be in this example here. We'll see. If not, I can probably use this as a reason to do that. Yes, it is in this example here. Actually, you can see. Good question. You're teaching the teacher. So in this example, we have like this passing grade classifier, where on one axis we have hours studied, and then on the other axis we have test pass. So it's good for a logistic regression model because it's either they passed the test or they didn't. Like we don't have like grades here, right? It's just pass, didn't pass, and then the hours studied. And you can see that there's overlap, right? Because people and problems are complex. You know, some people will study 3 hours and not pass, and other people will study 3 hours and will pass. And so this probability curve is usually good for those types of functions when there's like a little bit of separation. So you can see that, you know, there is some separation, even though there's overlap. You can see these are closer to this side and these are closer to this end of the hour study. So in this case, your model parameters are -3 is B, and your W is 1 for steepness. And so you can see that.
It's not -3 though. Yeah.
I think that's supposed to be a +3. Or I'm misinterpreting. I'll have to think about that. But this 3 is really where the middle of this is, right? I'm not sure if this negative gets distributed here, so I have to think about that. I don't know, actually. That could be. But either way, it is 3, whether negative or positive. It's 3 because of this +3 here. Mathematically, we can just abstract that negative out for a second. And so the reason that's there is because of this data set, because the way the data is dispersed. So if your data was dispersed differently, it really depends on what your X value is. So in this case, it's hour studied. But maybe if I did something else, like, what's another scalar value? Number of hours slept, right? Perhaps it would be different from that perspective. It would be a totally different midpoint because maybe most people sleep 8 hours, so it would shift it over to maybe like 4. But you don't have to determine those; your model will, which is nice. So, what does the model predict here? Just in terms of reading this graph, what do you think the model predicts for studying for 0 hours?
It's a fail, right?
It would predict 0 because that's where the line is down here. So if we come over here to the x-axis, studying for 0 hours, it would predict 0. What would it predict for 2 hours?
Oh, I see. I'm
10%?
Yeah, that's good. Somewhere in here between 0 and 0.25. I don't know what it is exactly. As we get 10% sounds like a good estimate here. 0.10 or 0.10. What would it predict for 4 hours?
That's your 50%.
Yeah, somewhere in there. It gets hard to read the graph at this point, but it'd be easier if I had lines on here. But somewhere around here, right? 75%, somewhere between 50 and 75%. And what would it predict for 8 hours? Yep, it would predict 1. So this extends, I mean, even though it looks like it's ending here, this extends to infinity. So it would predict 1 up here. This is the, some people call it the S-curve, otherwise called the sigmoid function or a logistic function. There's like 3 names for that. We can do that. I mean, this will probably be like a test question here. What does this model predict for these hours? And then like a picture of a sigmoid curve. So that's the level. If you want to like the gauge for what I'm looking for, if they're more like concept checks. Did I teach you how it works enough that you could answer like that type of question?
Is it a combination or is it multiple choice or?
I'll probably do multiple choice. It's up to you. What do you guys prefer? I lean multiple choice just because then if you went way off like on a rabbit hole, it's like a sanity check and you're like, whoa, okay, it's not that.
Okay.
Time, then at least I know it's 25 questions a night, but already wasted 15 minutes.
Yeah.
Not wasted.
Yeah.
But invested 15 minutes or something like, if it's only an hour, give you another example. I have to know.
I am planning 20 to 25 questions, 1 hour. So it's about 2.5 minutes per question. However, it's not like the time's up and like I ring a bell and you have to hand it in. Like if it takes you another 15 minutes, another 30 minutes, that's fine. I probably won't stay like another hour, but do like an hour to an hour and a half. I'll put it that way. Your computers are at your full disposal. This is not a, lock down your computer desk. You can Google stuff. You can use the internet. That's the point of this course, I guess, is so that you could use the internet to find those things. So logistic regression predicts a probability, right? We talked about that. So we said 10%, and then we said 50%, and then we said 75%, and then we said 1. So it predicts a probability. Well, how does that turn into an actual prediction? How do you know now I should predict someone will fail the test or won't fail the test? And so it gets to this point of decision boundaries. And in this case, we have age and length of hair and male and female. And we talked about this last time, but this is just to put another emphasis on it. When you make a probability prediction, you then have to make a decision against a threshold. And our default's 0.5. So if it's greater than 0.5, it's class 1. If it's less than 0.5, it's class 0. And so let's see. In this picture, this is a decision boundary. This is a way of making a decision. Anything on this side of the decision boundary is we're classifying male, and anything on this side of the decision boundary we're classifying as female. And we might measure accuracy as a number correct over the total. So we would count all these up, see how many we got correct. You can see there's going to be 2 incorrect in here, and then divide that by the total. There's going to be 2 incorrect on this side. But I won't go through this. Don't need to know this for the test. It's kind of somewhat interesting to me. But the decision boundary, how do you determine that? Like, how do we know that right here at this point it's the decision boundary? And maybe that's easy for us to do in 2 dimensions, but once we get to 3 and 4 and 5, it's really hard to decide that decision boundary, to visualize that. So how to quantitatively assess it? I'm not going to say anything other than this first line and this last line. So this first line, what's interesting is and it takes us way back to like elementary school algebra, right? Where when you want to solve for something, you put the answer on the other side of the equation. So if we want the probability of 0.5, we want to know that's what this decision boundary is. It doesn't know whether the model can't decide whether it's male or female, right? So that's because it's hitting that middle threshold, right? That exactly 0.5. So it's hitting this point right here. So that's what the decision boundary is it's exactly 0.5. So we want to know for our model go back down there, exactly 0.5. What's interesting is you can put the answer 0.5 on the output side, and then you can backwards solve. So you can put your formula in here and then solve backwards for what your weight and your bias will be, for what your beta sub naught, beta sub 1, beta sub n will actually be for that. So then you get this formula down here, but that tells you what your beta is and what your x sub 1 is. You don't need to know that. Interesting thing about decision boundary, you can solve for that. I thought I was going to say something else about decision boundary.
So when you're saying like the half,
Yeah.
someone just said, you know what, I'm just gonna try to figure out the half point and then go backwards. So at least I have some type of answer, and then maybe I can figure out what this means. I feel like it seems like an easy way of saying like, let me figure out what this looks like. You can use this as a formula.
Yeah, so this will be after your model is already trained. So I gave it all of the housing data, and it ran through its algorithm, maybe gradient descent, in order to determine what are these beta sub. So how many bedrooms? Is it 2 times the number of bedrooms? Add X amount of dollars to your house, and so it'll have already found all those weights. So you'll have this formula that'll be like 1 over 1 plus e, sorry, I changed my mind halfway through this. 1 plus e to the negative, let's see, 6 plus 7x. And let's say that we just have this data set. That's our y output, our real true y, so it doesn't have a hat on it. And our x features 0, 1, a, b, whatever. So this is our formula, and what you're asking is, I want to know, when does my model predict 0.5? And I want to know for what values. So you could set this equal to 1/2, and you could basically solve. In this case, you're going to solve for x. And just trust me that you can do that. And then what you would say is, you'd say, oh, well, when x equals b, then y equals 1/2, for example.
Got it.
I don't know if that's true in the
Right.
formula I wrote, but probably not. Yeah. Let's see. Okay, I think that is all I had for logistic regression. Let me double check my notes here. Hold on. Yes, okay. That's all I had for logistic regression. We're at 7:03, but we got a little bit of a late start, so I think we can, you know what, let's jump to our breakout, because I promised you we would try to apply the logistic regression to the fraud data set. So this is the data set you're going to use to train a final model object. So you could do that exactly with a logistic regression, and you could submit that, and that would be fine. So let's go find this data set. Sorry, I clicked it. There it is. So you will probably need to download this data set, and then you're going to want to move it to a location of your choice. So in my case, I'm going to move it to that regular location that I have all the other stuff at. And then I can just upload it. And if you guys are interested, you can just download it from my repo if that's easier for you. So here is this. Oh, it's a big data set. It will take a moment. I don't know if I can put this on Git. It might yell at me. Okay, that will take a second. So in the meantime, I make a new notebook. Let's go new. I don't have a notebook for this. Then we're going to call this fraud logistic regression. Oh, there we go. Archive 1. Looks like it's a zip file. You'll have to unzip it.
I unzipped it on my end, and then it shows up for it under
Maybe we have to.
structuring.csv.
I will upload this. I gotta make a new Finder tab here. 1 second.
Maybe this is the other one. Maybe we can.
Or it comes out as a. Yeah, I did that, yeah.
Let me extract it.
I did too. I saved it in my poster.
Here, let us start.
Oh, where is that? Okay. We're gonna move these to the trash. Oh wait, not yet. Okay.
I will.
All right.
Yeah, I have two of them, yeah. And that's only one of them.
Oh, okay. Oh, you put that? I don't think anything, because it's.
So I added that to my poster.
All right. If you check this repo, it should be, what did we call that? Fraud training.
See, let's go to the.
Why do I not see this?
Where is it?
I think it just took a while.
Oh, it's
It's
still,
just taking.
it's just- take a minute. I'm only at 90% here, so. I was worried about that. It is not gonna let me upload the file. It's too large. I thought that was gonna be the case. I'll drop it on Slack. Let's see if that'll work. Slack may yell at me too. I feel like I'm just gonna get. This is probably not gonna work.
Because of this one? Yeah. Is that how you call it? I might be different from
I got it when we sent it to this call.
that. I have it in there.
I'm uploading on Slack. It's at 17%, so it'll be a minute. It will not let me upload to Git, so that's not gonna do a thing. Should time box this. Let's
Oh, it's,
– 72%. Yeah, let you know. Well, if you guys remember, you're going to want to do your import functions, and then step 1, we'll just read in the data, import df equals pd dot, I assume this is a CSV, I guess I didn't really look.
it should be.
CSV, yeah.
Okay, good deal. And we called it fraud train CSV, so that's what it's called at least. So you want it to be fraud train.csv. And we can do df.head, we can do df.shape. And we can see this is why it's taking so long. It is 1.2 million rows, so it's a decently sized data set. It's got 23 columns. We can do df.columns, and we can do like df.b types. We can see what kind of types they are in these columns. We can see that we have like kind of a variety of like transaction time. Oh, look, I see I have like kind of an unnamed column. I can do like, I think I can do index equals 0 for that. No, not index. There's a way to get rid of that index column. Read CSV. Let's see. I don't remember exactly what it is. It's index call. That's what it is. Equals 0. Let's see what that does. See if that takes away that weird index. There we are. So that weird, I don't know, I'm getting a warning here. That's okay. That just means it's telling me something could be wrong, not that something is wrong. So that puts this index call here. So you can do that. Index call equals 0. You get rid of that like little extra index column there. So you can see there's a bunch of features here. You don't have to use all of them. You can use as many as you want, but you can see that our is fraud, that's going to be our Y target variable. So maybe we want to pull that out. So maybe we want to do split into train. There's a lot here, so we can do train validate test. And that's going to be something along the lines of, we're going to want to import train test split from sklearn. Here we are. We'll figure out how to do that. You scroll down here. Here it is. Grab this import function. Pop back over to our fraud notebook. Put that at the top. I like to put all mine at the top of the file. Put it wherever you want. And let's apply train test split. Let's copy this code. Good deal. So first we need to split into X and Y data set because this is going to require X and Y. So we'll say that X is equal to df.drop, and we're going to say I had copied this and then I copied something else on my keyboard, is fraud. So let's drop this. So our X data set is everything except the is fraud column, and our Y data set is equal to df at is fraud. So it's exactly the opposite. It's just the is fraud. I might have done that slightly incorrect. Is fraud. Axis equals zero. Axis equals 1. Exact syntax gets me at times. One of these. Specific column. Here we go. I switch back and forth between, yeah, that's if we're passing a list. Yes, we can just pass a list of one. I thought we already tried that though. We had tried that with this one. Oh, maybe it's because I don't think drop is done in place. It shouldn't. But we can validate here. Run df.head. No, it's not done in place. Oh, it's yelling at something else I did. I forgot my parentheses here. There we go. It's fraud. It's not founded. Oh, for drop. So that first one's correct, I believe. Oh, that's my axis. Please. Here we go. Okay. Sorry about that. I don't know why that took so long. Okay. So our Y, we want to separate out that is fraud. So for our Y, we're selecting just where the data frame is fraud. So Y, it's just the one column zeros or ones. And then X, we're dropping our target variable here. So we have our X and Y. And in this case, we're doing test size equals 0.33. That's probably fine. We're going to do, we're actually going to do train test validate split. So I'm going to leave that as the test set, but I'm going to call this X train validate. And I'm going to call this Y train validate. And I'm going to pass down here X train validate and Y train validate. And arbitrarily, I'm just going to change this to just 20%. I'm going to make it a smaller portion of the data set. Put this on the next line. There we go. Still see that? Me too. There we are. And this will now be our X train. Instead of X test, this will be X validate. And Y train, instead of that, this will be Y validate.
Can you explain that a little bit, just to make sure?
Yeah. So we have our X and our Y here. And what we want to do is we actually want to split this into 3 data sets. Unfortunately, the function that we have, train test split, only splits into 2 data sets. So we have to split into a test set and then a data set that we're then going to split again into 2 more data sets. So if I draw a picture of that up here. Let me just take a picture of this green thing and then I'll erase it. That way I can share it in the Slack chat. But here, I can do a picture. So we have our function. Unfortunately, what we want is 3 data sets. We want a training data set, a validation data set, and a test data set. Unfortunately, our function only splits into 2. So we have all data here. And we're going to split this, all data, into our train, or I'm sorry, in my function, into our test set. And we call this 33% of our data in that exact implementation. And then we're going to make this one our train validate set. At the other 77% of our data. And then we're going to split this one, this train validate set. This one's good. We're going to split this into our training set and our test set, or our validate set. Sorry, I keep messing up all my words today. Validate set. Training set at our validate set, we set at, this is 20% of 77%, just so you know. So it's not 20% of our entire data set, it's 20% of 77. That cord, what happened? Oh wait, it's like doing a weird dialy thing.
Computer died.
Oh, my computer died. I didn't put it in. Oh, I forgot my
Well,
code
tell
too.
your computer died, just say technical difficulties, don't ever tell them. Please just write that.
Are you put it in the chat?
Me?
Or,
Yeah.
here we go. Well, I was gonna ask if you were, because I had
Technical.
Somebody left this here. I don't know who did, but thank them. Well, there will be a moment because I'm sure it's like dead now. If somebody could just maybe turn on their audio, I'll just keep talking. Actually, let's do a.
I
We
can hear you.
Oh, good. I was worried. I thought my computer died. How can you hear me?
You're frozen, but we can hear you.
Strange. That's good. Let's maybe just finish what I was saying here, and then we're going to do a 10-minute break. It's halfway through thought. So then we have a training set here that is now 80% of our 77%. So it's not 80% of all the data. It's 80% of the 77%. So you'd have to multiply those together to figure out what percentage of the overall data set it is. But this is how we get our 3 data sets. So we have one here, our test set, our validation set, and our training set. It's unfortunate they don't have a function that can split into all 3 right off the bat. Yet. I think that's going to be the next thing. If you want to be like a open source code contributor, go contribute that piece of code. That would be really, really handy. sklearn's an open source package, so anybody can develop things for it. But yeah, so it's unfortunate you have to apply it twice. So this is us applying it once here. We'll apply it once. We'll apply split. I guess it's actually at that split that we apply that. So we'll apply train, test, split, and then we'll apply it again here. Okay. So that's the visual to match the code. And I'll take a picture of that. Drop it on the chat. Sorry for you guys on the phone, you can't see, but I will share a picture, so. Oh, you know what it was? You know why my computer stayed on?
Because it's streaming.
I think Mac has this like clever thing where the first couple seconds it dies, it doesn't actually die. It's like you have like 10 seconds or like a minute to like plug in your computer and it will come back. Like a half, like 0% isn't actually 0%, except my connection to this. I cannot get it to show up on the computer. There we are. Technical difficulties. Nice. There we go. Here's StreamYard. Get this back up. Am I sharing? No. Let's go entire screen. Let's go. You guys got to see my list of grad programs I'm applying to. Let's see. There we are. And okay, so I think that is, I wanted to take a break anyways, so that is actually good timing. Let's take a 10-minute break here, and then we're going to come back and talk about non-parametric models and decision trees. I think where we got in this, with this fraud data set, there we are. Pull this back up here. Let me run this, make sure this works. I'm not giving you bad code. That happens. So we do have this. We can do xtrain.shape. We can just validate x. Validate should be smaller than train. And our x test. See, I think I made a mistake. Wait, no, that's smaller. Okay. And our x test should be larger than validate. Let's just validate all those things actually happened here. Yep. 400,000 is larger than 173,000. Our validate should be the smallest, and then our largest should be our training set. Okay, just want to make sure I didn't swap something around there. Weird. So this is your train test split data set, and then from this you would want to apply. We could like apply our logistic regression model, or apply your grid search, or whatever you wanted to do next. So for that, we would just go to sklearn, logistic regression. Oh, there we are. And we're going to import this. Same thing we've done before. I'm just going to put it here because I'm lazy, but you should put it at the top of your file. Formatting. And they call their CLF. Sure, we'll call it CLF. And we're going to pass it X train, Y train. Sure, we'll set that random state to 0. That's fine. Oh, yes. That is probably not going to work, right? Because we didn't do anything to all of our textual data, right? We talked about how we're going to have to apply transforms to this, so you're probably going to want to set up a pipeline just to show you that logistic regression will work. I'm just going to pick one column. We're just going to pick amount. I saw that in there. It looked like it was mostly just binary, so we're going to do xtrain at amount. Here we go. Um, all right, just to show you, I'm training a logistic regression quite literally on one column, so that's maybe not what you want to do. Technically, it will work. Technically, you could submit that would be fine, but you maybe want to add a few other columns. So then I'll just show you that the predict function works here. So now we're going to do this predict function, but instead we're going to pass x validate. But remember, we only pass amount to training, so we can only pass amount to validating. So whatever columns you pass to your training set, when you call predict on your model, it has to be that same column. sklearn also has this function called predict proba. So we talked about how under the hood, this is a sigmoid, and they're all just probabilities. You can call predict proba, and you can get your actual probabilities here. So for this one, this first value in the x validate set, which would be, let's look at it. For 6.97 as an input, our model predicted a probability of 0.995 for the zero class. So if we think about the S curve in our head, 0.697 is really, really close to that zero. Sorry, this way is really, really close to that zero. Yes, so these are the basic functions. You might want to apply some transformations to some columns in order for them to have numerical values. We went through that in all the pipelining code. So this is the actual logistic regression function. Okay, I don't want to waste any more of your time, sorry. 10-minute break, 7:40. I'm back at 7:40. All right, so we're having a conversation about why 42 is kind of the default random state as you search the internet. And we touched on this last week. Like I said, it doesn't really matter what number you can choose. You saw later in the code we chose 0 as our seed for our random state. So we just looked it up, and there's this Medium article that referenced The Hitchhiker's Guide to the Galaxy. Basically, it's a giant nerdy internet inside joke to use the number 42 for the random state, because there's this like science fiction sort of theory that 42 is the answer to life. And then they have a bunch of these things here. So
There's a couple of things on the private chat. It says, John says, can we see the bottom section on code? And then James says, I'm here if someone could let me in. I'm assuming on the stream. Because he's not on.
oh yeah, I hope he's not downstairs. Did I not? That's
No, he's usually online.
Fine.
okay. Perfect. Oh, there you are. Gotcha. Sorry, James.
Yeah, I was like, we let type in person, not
Okay, let's see. So I think we're going to do mostly whiteboarding here for the decision tree algorithm. I just think that's going to be the easiest way and tangible way to approach that. And there's a lot of things here. So we're going to go a little bit ad hoc here. Let me see if I have anything else interesting to say. 1 second. Oh yeah, here's some. Okay. I think I'm going to start with some limitations of linear models. So we talked about linear regression, and we just talked about logistic regression. Now note, because logistic regression is based on that linear formula, it's something called a linear model. So I'm going to jump a little bit to a concept we haven't talked about a lot, which is image processing, but I'm just going to use it theoretically to describe why linear models have a limitation. And the limitation is basically that the linear models don't know the relationships between the other features. So kind of in the traditional sense, when you're building like a linear regression model and you're building it for like a house price data set, you might want to try a bunch of different transformations. If I take the size of the house times the number of bedrooms, is that a new kind of like more powerful feature, right, that I can add into that model that has some information within it that wasn't in there before, with the kind of features being separate together or separated out. So linear model doesn't look at the relationship between each of those features. It just looks at each feature independently and decides kind of that output or impact that it's going to have on that data set. And it's kind of hard to wrap your head around that. A really insightful thing for me was when we were thinking about image processing. So we had that MNIST data set, right? Let me pull it up because this is not we had our kind of MNIST data set over close. What was it called here? Our fashion data set. Right. We had our fashion data set, which we didn't actually use. We just talked about it. And a bunch of t-shirts and pants and shoes and purses and all such things. When you train a model, like a neural network, over this, what it actually does is it takes that picture and it separates it into a grid. So each pixel is one feature. So just like number of bedrooms might have been a feature input into our model, we could say the pixel in the upper left corner is one feature, the next pixel over is another feature, the next pixel over is another feature, and so on. And when we do it that way, we can either say the pixel is it is a black pixel or it's a white pixel, or maybe it's like 70% white, or maybe it's 30% white. That's how you get this kind of like grading of colors, and that on that scale, on that sigmoid curve from 0 to 1, how white or how black is it? So instead of going from 0 to 1, we're going on a grade of scales from black to white. And you would do that for each pixel. Okay. So what I'm trying to say here is when you train a model to recognize these images, and you're just telling it kind of that one pixel at a time framework that we talked about, a linear model, then this model can do things and have certain weights applied to certain pixels. So it'll say, hey, these pixels are important. They have higher weights in our models. So our parameter, if we scale all our values, the higher the weight, the more important it is. So you can see kind of this grading of importance. For pants, it looks like over here, and for coat, it looks like over here, and dress, you can see maybe is a little harder. Pullover, it's really important, these edges over here. So the downside of using a linear model is it's treating each of these pixels independent from each other. So this pixel is just cares about in my training set and all the history that I've seen, when it's been a shirt, how bright or how dark has this pixel been in the past. That's all it cares about. It doesn't care about the pixel above it, the pixel below it, the pixel next to it. It just cares about itself. And that's the downside of linear models, is when we come to look at things like images, things like relationship and structure and the relationship to the pixels near you are really important. So in images, something that's very important is the concept of an edge. So how starkly does the contrast change from one area of a photo to another area? And that is where linear models just aren't able to perform. They cannot detect like an edge because they are unaware of the relationships of the other pixels around them. So edge detection, this is just an example of what that might look like. So you can see there's a really stark contrast in color change here between the tree and this hair. And it detects that as an edge. So there's really not a lot of like color change. If I look at, the colors around this area, the average colors around these trees, they're going to be approximately the same. And that's what you'll get here. And you don't need to know about any of this other stuff, but just trying to show the importance that linear models have a limitation where they wouldn't be able to do this type of technology. They wouldn't be able to detect edges because they're not aware of the relationships of itself to other features in that matrix. So it depends on the problem that you're trying to solve, but that is the biggest limitation to linear models, is that they're kind of, each feature is sort of isolated by itself. We are combining all those features for a prediction, but we're not taking combinations of those features in that prediction. Okay, I think that's all I wanted to say on that piece. So that was a limitation. Oh, non-parametric models. So non-parametric, I don't have a slide for this, so we'll stay on here, I guess. Non-parametric, all that means is there are no parameters in your model. So we're not creating a mathematical formula for this. You already know a non-parametric model, which is k nearest neighbors. There's no weights or parameters or formulas that we're trying to train. So a decision tree is another form of something that's a non-parametric model. These are parametric models. So linear regression and logistic regression will be parametric models. They have parameters that we're hypertuning. Neural networks, which, hint, hint, are just, this is a gross oversimplification, but are just a series of logistic regressions. So truly they are. That is a non-parametric model. If you want a little tangent for just a second on, now that we just learned linear regression, so we're going to build a neural network here, okay? We're going to have, let's make it 2 nodes. So we have 2 nodes in neural networks sometimes.
Can you make your screen?
Oh, yes.
Sorry.
Nope, you're right. They can't even see at all. I'm a tiny little window. There we are. So let's think about, just take a side tangent for a second, think about neural networks, just some importance of logistic regression here. So all the things we built to, very important, right? They all build on each other. And so neural networks here will have let's say an input layer. There's, you don't need to know what these are, but basically in neural networks, there's this thing called an input layer. Then there's usually a bunch of stuff called a hidden layer. Sorry, I spelled that weird. And then there's like an output layer. And when we are, let's just start with an input and an output layer here. Be simple, we're gonna skip the hidden layer. When we have neural networks, you'll see them a lot, like kind of like maybe this type of, maybe they'll have arrows, maybe they won't. But basically, each of these will have something called a W associated with them. So this will be W2, and then that is put into our neural network here, and this is going to apply a sigmoid function to this input, and this input is going to be x times W1 plus x times W2 plus b. So there's going to be a b, or otherwise called in neural networks a bias, but it's the same thing as this, which is the same thing as this. So it's our beta sub naught, it's our intercept. So there's this bias term here. And then there's a sigmoid function that normalizes that output between the probability of 0 and 1. And so what this, I don't know how coherent this is, because I didn't think I was going to talk about this, so sorry if this is a little messy. But last thing is when you add, so say we have a bunch of, a couple more, we could go, what this will look like. And there we go. So basically here, let me just pick a color. Here, we're going to have a sigmoid function and a bias, and we're going to have this weight, all these weights. That come into that one. And here we're going to have a sigmoid function and a bias. And I'm going to call these, I'm going to call them W. I'm going to call them A. I don't know why, but I just call them something different. A1, A2. You can see it gets really messy. That's why it's confusing. But the A's are going here, the W's are going here, and we'll call this C. And a sigmoid function and a bias. So when I probably poorly say that neural networks are a bunch of logistic regression functions, and they sort of are. You'll probably be made fun of if you say that in the real world, so don't say that. But there's a lot of more complexities in there. You can change sigmoid functions to be something else, and there's I have a really, really cool website I'll show you that's neat for showing how to play with these. But this is the whole importance and the reason why we spend so much time on linear regression, because it's in logistic regression, why we spend so much time usually on logistic regression, because it builds neural networks, so it's kind of that conceptual foundation. But yes, so all these weights and biases, so you'll kind of hear that, you'll hear that a lot, weights and biases, when you talk about when they talk about neural networks, and that's all these. So these are our weights, our B sub 1, B sub 2, B sub n, and our biases are our B sub 0. There's just a bunch of them in neural networks. So this has weights and biases, this has weights and biases, this has weights and biases. Okay, that's all. Now that I wasted our time, sorry. We can get back on track here. Non-parametric. So that's why that's parametric, because all the other ones are parametric too. Decision tree algorithm. Okay, this is super, super important. I am now going to erase the board, but I'll take a picture here first. You know, that's a good idea. Maybe I'll use the flip it over. I'm like almost doing that the whole time anyways. Might save us a few minutes of me trying to erase this. See how this goes. There we go. Hey, somehow that actually stuck. Okay, so decision trees. They're really such a natural concept to people because at the heart, what a decision tree, oh, I was going to pull up a picture, I'm not. What a decision tree is going to look like is I have a piece of fruit and I want to determine, is this a banana? Kind of looks like a moon, but I want to ask, is this a banana? And you might, you ever play 20 questions? You try, that's a decision tree. You're making a decision tree in your head. Somebody's like, I picked something, and then you think about a question. You ask, is it a person or not a person? And they'll say, well, it's not a person. Then you just eliminated a whole bunch of things that you would have asked, right? And then you think to yourself, okay, it's not a person. And then you think, is it a thing or not? Is it a place or not a place? And they say, no, it's not a place. It has to be a thing, right? Person, place, or thing. Those are the things you narrow down to. So now you're like, okay, it's a thing, and then you can keep going down that tree. That's exactly what a decision tree is. So if it's a banana, something we might ask if they give us some type of fruit, let's say, and they want to know, is it a banana? We might say, is it yellow? And we can either say, yes, it's yellow, or we can say, no, it's not yellow. And maybe if yes, it is yellow, so maybe if they say no, it's not yellow, we just say, it's not a banana. Let's pretend that all bananas are yellow here. I know there's green bananas, could be on right. Let's just say it's not a banana. That's supposed to be an exclamation point. That's our decision. But maybe if it is yellow, we still ask questions because apples can be yellow and mangoes can be yellow. So just because it's yellow doesn't mean it's a banana. So then maybe we ask if, I don't know, I can't think of another question. We can ask, is it round? There we go. So now we ask, is it round? Like roundish, you know? Like, because if it's round, yes, well then, it's not a banana. It's an apple. Let's say banana's oval, right? Let's classify this as oval or something. You get the concept. And if you say no, maybe we ask another question, right?
Is it edible?
Can you bite it, right? Can you bite it and does it taste good? So can you bite it? And maybe we say no. So maybe we say yes, then it's not a banana. And can you bite it? No, maybe that we can still, and then it's not a mango, right? Because the mango would have been round. And so we say, now we decide, okay, it's a banana. I'm going to use this for actual class today, so we're going to appreciate your help with that. So basically, we're going to make a data set, we're going to make a decision tree that uses data like this, and these are our zeros. So this is when we're saying it's not a banana, and this is going to be our one. And this is truly what a decision tree is. This is the foundation of random forest, the foundation of gradient boosted trees, which we'll get to. Okay, so how does it actually do that? Like in our head, intuitively, to us, that makes sense. But first we need a data set, because that's what we need to train all models. And we need what fruit it is. Remember, this is our training data set, so there's labels. This is supervised learning. Remember, supervised versus unsupervised test topic. So we have fruit, and this is, we can have a banana. And let's just do, for simplicity, because I don't want to get into multi-class labels, just do banana, not a banana. So we're going to do not here, banana. And it's either a banana or not a banana. And one more, maybe not a banana. Okay, this is going to be our data set. And remember, these, when we transform these because, remember another test concept, our models can't take the textual data. It has to be transformed. So this is our 1, 0, 1, 0. So that's what it looked like under the hood. And then our fruit, let's add some attributes about it. So what's the first thing? We ask what color it is. That's the first thing we ask. So let's say that this one's a banana. All of our bananas are yellow. And I'm realizing I'm going to add another. I'll just put it up here. Remind myself later. We'll keep working. Sorry. What's the next question? We asked, is it round? Round. And banana we said was.
Yes or no?
Yep. No. No. Yes. 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 We're going to fill in some other colors here. Let's say this not a banana is a red apple here. One of these is yellow, but it's going to be a yellow apple. And then I want to make sure that we're getting good. Can you bite? Oh, one of these is a mango. So let's say it's a yellow. Let's say it's a yellow mango just because I want to get to the bottom of the tree with it. So it's going to be weird. Then what's the last question? Can you bite it? Bite it. Let's see, our yellow mango, oh no, that got filtered out at round. Can you bite it? What we're trying to decide on at the bottom with bite, banana versus I don't know, I don't have anything here. I'll just make one up. Can you bite it? Yeah.
You can bite an apple through the surface, but you can't bite a banana through the surface.
Oh, there we go. It's carrot. There we go. The problem with the apple, I agree with the apple, but I think that'd get filtered out as round over here. So I think it'd be not a banana. It's going to be a carrot, okay? Maybe I should write these down next to this. Okay. So this one's maybe like a carrot. And we said this was a mango. And we said that this one was an apple. Okay. So can you bite it? Yes. And mango, so all our bananas are going to be no here. And let's see, the apple, can you bite it? Yes. And the mango, can you bite it? No. Okay. All right. Sorry for that. Had to make a data set. So now we're going to train a decision tree. And basically, we have this data set, and the first step of a decision tree, running out of colors. The first step, oh, there's that one. Step one is going to be that we need to decide a column to split on. So first, we're going to look at this data set, and we've got all these options. So this is our y hat, and this is our x sub 1, and this is our x sub 2, and x sub 3. So we could split on any of these x's, but we don't know which one has the most value. And this gets to the point, what is the whole purpose of a decision tree? Well, we want to have complete 100% separation. So when I ask a question, if I know for certainty that that separates the data set cleanly into two sets, that's the feature I'm going to choose. So I made this kind of side note here to say STEM, or I guess STEM is a bad thing. Can you peel it? There we go. Let's assume that you can't peel a mango, carrot, or apple. Let's just assume there's some feature that perfectly distinguishes a banana. That would be our ultimate goal, to say that for every representation of banana, for everywhere that I have a 1, there is some feature that is always maybe a 1 and a 0, some feature that maps exactly, so that if I ask that question, if I asked a question here and I created a split, that on this side of the split, all of my data would be of class label 0, and all of my data over here would be of class label 1. So that's what a perfect split is when I ask that question and you tell me yes or no, when I separate my data based off of that, all of my data goes here is of one specific class, and all the ones over here are of no other of another class. There is no mixing of the classes. And you'll see what that means in our example as we work through this. So that's our objective. Our objective is to identify a split that perfectly mixes, creates separation between the columns. So we need to decide a column to split on. And our objective function for that we're going to discuss here is our Gini impurity. So we want to minimize impurity, right? If you have more than one label in a split, that's impure. And so we want total purity. We want to separate them completely. And so we're going to look at each of these columns. So we're going to look at color. So let's look at color and how that relates to this feature set. And we're going to look at this and we're going to find out if we did that decision tree correctly. So this will be interesting. So we see that banana and yellow, and banana and yellow, and then we have banana and not yellow, and banana and not yellow, and then not banana and red. So we clearly don't have 100% separation because there are yellows associated with both banana and both not banana. And so what we would do is we would take the probability of when we see banana that it's yellow versus the probability of when we see banana that it's not yellow. And maybe I won't write all of that out, but then we would look at round and we'd say, okay, let's look at round and let's see when the banana is round, it's always no for banana. It's always no. And then for not banana, it's always yes. And for not banana, it's yes. And for not banana, it's yes. So fun fact, we would actually, we made this as our decision tree. That's actually based on the data we created. The first split we would choose is actually round because it perfectly separates the data. I didn't even need the peel it one because I guess we labeled our carrot as round. I guess we could change that to a no here and that would make it maybe better. There we go. There we go. Then we have bite it. So can you bite it? And we have not banana, yes, not banana, no, not banana, yes. So there's a lot of mixing there. But for the banana, all we have are no's under the banana. So that's probably a good separator if we don't use, it's about the same. So round and bited are going to be about the same in terms of separation. Okay, so first thing.
Question, if I may.
Yeah.
So if you're trying to make this a generic training session for different types of fruit, you wouldn't be able to ask this one if it's a banana, but you're going to be able to ask it later on if it's a mango. You're saying we need to choose very specific things as part of our split so that we minimize impurity, but mango would have a entirely different set of impurities than bananas will, potential.
Oh, absolutely. So for this one that we're training, if we're calculating our impurity with just the 0, 1, our model doesn't know there's like a carrot or a mango that it might make different decisions on. So in this case, I oversimplified and made it binary. But what you really want, if you want to generalize it, is to make it say banana, apple, mango, and then you would want these labels to actually be 0, 1, 2 in your data set instead of treating the apple the same as a mango, the same as a carrot. it would, the algorithm would then be able to look at the splits. So it would, I tried to do this because it's simple, but if we think about this one, what's going to happen is it's going to do that same thing, looking at that same column, but comparing that separation across the different classes. So comparing it across mango. In this case, we only have one example of a mango, but imagine we had a bunch of different examples of a mango. Maybe mango has a better way, it creates more a more pure split for mango than it does for banana, so that it would choose that one instead.
Okay.
That was a really bad way of explaining that. Sorry. I'll share something that will maybe explain that better. Yes, this one is trained just to the 0, 1. Is it a banana or not? It'd be terrible at other fruit. It would be awful. It doesn't know that something exists that isn't a banana. It just treats everything as not a banana the same. Okay. So the first thing we're going to do is we're going to choose a column, and I was going to have you guys implement a decision tree by hand, and the reason, one of the many reasons, other than the inordinate amount of time I spent on it, trying to do that myself, and that I was not going to have it is because I realized that this uses a computer science function that you may or may not be familiar with called recursion, which means it's going to call, it's a function that's going to actually end up calling itself over and over and over again until it kind of like reaches the end of that. I felt like that was like a little too complicated, which is saying something because I feel like I give you guys some complicated stuff. So anyways, what this is going to do is it's going to iteratively continue to look at it. So let me take a step back. So the first thing we're going to do is we're going to decide a column to split on. And if there are no columns, if no columns decrease in purity, so if we looked at all of these columns and they were either all exactly the same, or we had perfect impurity, or they didn't have if they didn't contribute to decreasing that impurity, we would stop. So that's how you know you are done. And so if we do decide a column to split on, then within that column, so in this case, I made it really simple and just tried to give you 2 categories. It either is red, and if it's not red, then it's yellow. But in reality, there's a lot of values, right? You can have 2 bedrooms, 6 bedrooms, 10 bedrooms. So even if you have like number of bedrooms, you have to decide where within there to split on. So then you have to decide the value to split on. And again, the objective is to minimize impurity. Okay. And then once you determine that value to split on, so all of that work is just to select, is it yellow? Once you do that, this is the important part. Once we make that decision, we calculate that Gini impurity that minimizes the mixture. And so we have as much separation between the 2 classes as we possibly can. Then we're going to pass the split data set to each node. And 4 is we're going to repeat. So when I said recursion, that's what I meant. We're going to come back up here, and we're going to do that for each node. So let's go to the other side of the board, see what that looks like. So there we go. So let's think about this whole data set. We have 1, 2, 3, 4, 5 rows. So we have our entire data set. And this is 5 rows. And let's just, let's use our example over here just because it's easier. let's say we split on is it yellow, or color equals yellow. That's how you'll see it in the code. So if our color equals yellow, you're either going to have a yes, the color equals yellow, or no, the color does not equal yellow. True or false, I guess, maybe is a better way to say that. It's either true or that's false. So if the color equals yellow, we have 4 records where the color equals yellow, right? So now this is our data set where the color equals yellow. And that's only 4 rows. And this is our data. I'm just going to abbreviate to data, where color does not equal yellow. And that is 1 row. Okay, so your first node to this node here, you pass all of your data. Once you decide a column to split on and a value within that column to split on, you are only from now on passing subsets of the data. So there's only 4 rows that are coming to this next split, and there's 1 row that's coming here. So let's talk about the 1 row. There's only 1 row of data. That means we only have 1 label. That means we have perfect separation. So there is 100% impurity, or 100%, 0% impurity here. Because we only have one row of data. We just have 1 record. There's no mixes of labels. We can't have mixes. There's only 1. So we're done. So in our decision tree, if your color does not equal yellow, then you're not a banana. Because we said this is a 0, not a banana. Not a banana. And you know what? I'm going to cross out records as we get done with them. So that was, maybe I better take a picture first. I started doing weird things. All right, we finished. Oh my goodness, this is really hard to. I don't like that one. It's better. Okay, we're done with that one. So the next thing we're going to do is now we have 4 rows. We only have 4 rows left on this, and now we want to know, with that other row gone, which is the next best column to split on. So you ignore the other data. You're only looking at these 4. So you see how the Gini impurity is now going to be different for this one compared to the Gini impurity at this node. So you need to go all the way through the algorithm again. You need to look at all the columns, figure out the highest impurity. Within that column, figure out which value to split on. In our case, it's binary, so there's only 1 thing to split on. But let's just say we ask the question, is it round? So round equals, so the next question would be round equals like true. And that's either going to be true, round is true, or round is false. Or I guess round equals yes, I guess is the. So is it round? Round equals yes, that's either going to be true or false. And if it is round, let's see, we have 1 not banana that is round. See, we have 3 no's and 1 yes. And so if it's round, then it is not a banana because this is going to be 1 row. See, now we're going to pass this. Let me get my black. Is it round? Equal yes. Of these, this is the only one with round equals yes. So that's the 1 row that we're passing to this one. And now we have 0% impurity. It's only 1 row. We only have 1 label. We can't be impure. Now we're done. We say, not a banana. And why do we say not a banana? Because the 1 row that we do have in here is not a banana. So that's why. All right, so now we now have 3 rows here. We have our data is 3 rows now. And we want to know, and this is just all the ones where round is equal to no, and color is equal to yellow. Okay, now we're gonna ask another question, and we're just gonna not calculate impurity, make it simple, and just ask questions we came up with at the beginning of class. And the question is, can you bite it? So does bite equal yes is our question here. So we're gonna ask, does bite equal yes? And that's either true, it does equal yes, or that's false, it does not equal yes. And if we look at these, there was one where bite does not equal yes. So we're gonna, or where bite equals yes, sorry. So that is bite equals yes is true. So that's that one record. And now we have one row. We have 0% impurity, and we're done. And now we have two rows over here, but both of those rows are labeled banana. So we have two rows, but they're both labeled banana, so we still have 0% impurity. And we're done with this node. And that means this one is labeled banana because both of those have the banana label in them. And that's the two rows that are in this node have the banana label. That's why that one's labeled banana. Everything else is not a banana. And we're done with the tree now because we have finished our final node. We stopped when we reached 0% impurity for this node. All the other nodes have stopped. We have nowhere else to go from here. There are no more, every node has 0% impurity. So we have nowhere else to go. Our decision tree is finished. So now you could give it a new record that behind the scenes was either a banana or not a banana. And this decision tree, you can see how well it does in telling you whether it's a banana or not a banana. And then this speaks to our concept of generalizability, right? This was our really small data set. And if you gave it like another fruit that you could probably think of that might not fit into these rules or boundaries, it might do really bad. Okay, gonna pause here for a second. Take a picture. That was a very oversimplified example, but maybe useful. How are we feeling about decision trees?
So when you're programming this, does the program automatically detect what the next decision should be?
Yes, so you won't have to do, I'm kind of teaching the concepts here so I can explain why decision trees are actually really poor and why you should use something called random forest or gradient boosted tree instead, which are actually very powerful. But in the real world, we'll just pull up sklearn and I'll show you guys that, and you'll just do import decision tree and you'll give it your X data and your Y data and it'll do all that for you.
Gotcha. The recursion, it does that too?
Oh yeah, yeah.
Okay.
And they're like hyper tuned. So if you go look at their code, like it boils down to like C code and stuff like that. So they're very efficient. I wouldn't recommend necessarily. I think it's useful to like understand the concept in terms of implementing it yourself, but practically you don't need to at all. Let's see. Things I didn't mention here. So, a couple of things. I realized after I did this example, I probably poorly maybe implied that one row is equal to 0% impurity, and that's not true. I hope you guys know that. You can have, like here I had two rows, that's still 0% impurity. Or you don't always have to get to a split where it's just one row. There might be 10 records here and 12 records here. Okay, I hope that was clear. I just picked an example that happened to be splitting off one row at a time. One thing to keep in mind with decision trees is imagine we had a really big data set, like the millions of records one we just pulled in, and we applied a decision tree to that. that might go on for a really, really long time. So when we talk about depth, that's one of the parameters that you might want to train or limit on your tree. And so this is a depth 1, this is 2, and this is 3. So this is a depth 3 tree. So we went 3 deep. You know, your tree could be hundreds deep. It could be super, super deep. If you had a lot of columns and a lot of different values, and it was really difficult to separate on them, you could end up with a tree that's like hundreds deep. And so that's what that's one parameter. There's parameters that you'll see on trees that you can change in like sklearn. One is depth, so you can do a grid search. We talk about grid search to figure out what is the right depth. You might want to try like 10, 15, 30. Those are like kind of typical like tree depth parameters that people search for, thumb in the air. And then another parameter in addition to depth is the number of records you need at a node. So maybe, for example, we say the minimum number of records has to be 3 at a node. So actually in this case where we split off one row, it would never make a decision that it's not a banana here, because we'd say you have to have at least 3 records in a leaf node. By the way, these each decision point is a node here, and then these are leaves. When we're actually kind of making a terminal decision here, we're able to like confidently say it is a banana or it isn't a banana. These are leaves, and then these are your nodes that split into leaves, and these are maybe sometimes people call these children. This might be called a parent. Let's see, what else? Min split at leaf. Yeah, there's a bunch of parameters. Maybe we'll just go look at the code from that. I think that's it for decision trees. Okay, let's go. What do we got time-wise? Oh, man. We're gonna go right into random forest. We're gonna run out of time. It's like 8:30. Okay. We're gonna go right into it. Let me look at my notes, see if Gini impurity, pros and cons. Okay. Decision trees, really cool, right? Super easy to like conceptualize. And if I went to a stakeholder and told them the reason that the claim, my model predicted the claim was approved was because they had this information with them, because it was this type of disability, and because they're of this age, they'd be like, yeah, that makes a lot of sense. Whereas when you kind of put some mathematical like numbers in there, like it's 3 times this and 7 times this, and oh, but there's this intercept too, it just gets harder to explain. So interpretability of these decision trees, excellent. The thing that'll, difficulty, the trouble with decision trees that you'll often see is that they get extremely overfit to your data. So they do a really, really good job of memorizing the exact patterns in your data, so much so that it's really not applicable beyond your specific training set. So they'll tend to perform very poorly in the real world because they're overgeneralized, they're overfit, or not overgeneralized, I'm sorry, they're overfit, overtrained, hyper-tuned onto your specific data set, where they're looking for, yeah, this is where it minimizes the impurity, but for your data set. And maybe when the data shifts a little bit and changes a little bit, it doesn't do so well. I want to see if I had anything else on decision trees real quick. So when you output a decision tree from sklearn, for example, it's going to look like this. It's going to say customer service calls, this is your column, is less than or equal to 3.5. Entropy, by the way,
We're not seeing it.
Oh, so sorry. Thank you. So customer service calls, this is your column. When it's less than or equal to 3.5, that's either true or that's false. And entropy, by the way, is a measure of disorder within a system. You might have heard that from like physics in the past. It's just another way of thinking of Gini impurity. I describe Gini impurity because I think it's the simplest metric to use for a decision tree, but there's entropy, there's Gini impurity, and there's information gain. And different algorithms use different exact calculations. So if you're super curious about what the exact metric, just like you can have different distance metrics, you can have different splitting metrics for decision trees. I would encourage you to look, but generally the idea, the concept of minimizing the number of mixtures in terms of your labels that you pass each node is the goal. So just a really important concept to remember is that if this says it's true here, it's taking the subset of data that meet that criteria, where the customer service calls are less than or equal to 3.5, and it's passing it to this node. And then where total days and minutes are less than or equal to 23.15, it's passing it to this node. So now each of these nodes have a subset of the data. They do not have the entire data set. So it's that's kind of the recursion piece there. Okay, we're not going to get into that. I think that's good. The random forest I want to talk about. Super, super important. Okay. All right, so we breezed through decision trees. I'm going to send out more on that because I wasted all my time talking about that. But I want to talk about the concept of random forest, and that's the power of the many. So I think this comes from this old story or paper, I can't remember, where people go around and ask, how much do you think this cow weighs? And okay, maybe you've heard of this. And people will give a bunch of different answers about how they think about the cow, how much the cow weighs. And pretty much most of the time, everybody's wrong, right? But if you collect like a distribution of their predictions of how much they think the cow weighs, it's going to look like something like this, where a lot of people predict too much and a lot of people predict too few, and in the middle we have how much this cow weighs. And that's it's very interesting, and it shows the power of the people, or I can't remember the exact terminology, I'll see if I can find it. But basically, the collection of the knowledge of the masses, something along those lines, the knowledge of the masses. And that is the theory behind random forests. And basically, the idea is, well, one decision tree trained over our entire data set is probably wrong. What if we trained a bunch of decision trees, but manipulated the data? Because if we trained a bunch of decision trees and just didn't do anything to it, they would all make the same decisions because it's just a computer science algorithm. But if we manipulated the data and shifted and shuffled things just a little bit, maybe we could get decision trees that make a bunch of, have different ways of making decisions on the data, and we can use that to kind of that power of the people sort of thing. So we have our data set here. And what we're going to do is we're going to sample, and we're going to sample in two ways. One, we're going to sample columns. And two, we're going to sample data, sample rows. And sometimes you might hear this called bagging. You might hear bagging and boosting. Boosting's for the gradient boosted trees, but or sometimes you might hear this called bootstrap sampling. But I think it's much easier to just think of it sampling columns and sampling rows. And so we're going to train a bunch of decision trees. So to decision tree 1, 2, 3, 4, decision tree n, each of them are going to get a subset of our sampling of columns and rows with replacement. With replacement means that if I sample column 2, I can put it back in my sampling set and think of all our columns are in a hat, and I shook them up, and I'm gonna take a handful of them out, and I'm gonna hand them to you, and then you're gonna build a tree with those. But I'm gonna take those little name tags back, I'm gonna put them back in the hat, I'm gonna shuffle the hat again, and then I'm gonna pull them out. So like for this one, perhaps we send it column A, B, and C. We can still send column A to this one over here. So maybe this one gets A and B, and maybe this one gets C, F, G, maybe this one gets F, B, you get the idea. So those, we sample the columns, so they do not receive all of the data. We also sample the rows. So maybe this gets rows like 1 through 10. It's really not quite usually that even, but you can imagine, like I have a bunch of rows, and maybe this gets, let me change that. Maybe this will get 40% of the data, and this will get 40% of the data, and this will get 40% of the data, and this will get 40% of the data. But it's with replacement. So we take 40% out, we put it back in, we shuffle our hat again, we take another 40% out, hand it to this guy. So there can be overlap and randomness in what these receive. So that's how we create these trees. And then what happens is these end up looking different. Right? Maybe this guy looks like this. Maybe this guy just looks like this. Maybe this guy just split once. Maybe this guy got a really difficult batch, and it was really hard for him, and he had to just keep going here. Right? So your trees end up looking different. So you get different ways of them making decisions on something. And just assume, I guess, each of these, by the way, are at the end of these little sticks here. You know these are either 0 or 1, right? They're either trying to, I can put little sticks there. Let's see. That wouldn't be a thing, sorry. Make these. There you go. So you get decisions out of this, and then where the power of, okay, we have all these different decision trees. How do you actually make a prediction? Like, how does a prediction come out of this model? Well, we'll give a banana to each of these, or we'll give a new picture and we'll be asking it, is this thing a banana? So now we're going to ask each tree the question separately, each decision tree, and they're going to tell us whether or not they think, and some people, they're going to disagree. Some people are going to say yes. Some people are going to say no. This guy's going to say yes, and this guy's going to say yes. And what we do is we take the power of the people. We just say, what did the majority say? It's called majority vote. And we're like, well, most people said yes, so we think it's we do think it's banana. And actually, we can take a probability here. We can actually say that 75% of people said yes. So our probability that it's a banana is equal to 0.75. This is random forest. A bunch of decision trees trained over a subset of the data and a subset of the columns and a subset of the rows. And it basically makes the algorithm more resilient. Now, here I have 4 trees. In reality, you're probably going to train 30 trees, 50 trees, 100 trees, 500 trees. So it's quite a bit of different ways of parsing up the data. And the reason this is so powerful, because the problem that we've seen in the past with decision trees is, what if you have a really powerful and predictive feature? What if I have one of those features that really greatly separates my data set? It's good sometimes to set that aside. So say A was a really powerful feature. Well, tree number 3 doesn't have A, or tree number 4. So it allows the importance of other features to be highlighted. So it's not just weighted totally on that feature. So in feature 3 and 4, you can see the importance of other features. And there's actually something in decision trees that you can, in random forest that you can pull out. Because your next question might be, well, how do I know how it actually made this decision? You know, I've got, I'm making these decisions on claims and the government's asking, how do you decide who's getting approved or not? How do I know if I have 100 different trees making this decision and I'm just aggregating the vote? You can take something out of a tree called the feature importance, and it'll be this visualization. It'll be all your features. You'll have A, B, C, D, and it'll tell you across all of your trees. So this is feature importance. Across all of your trees, how important was that feature? How critical was it in creating this split, and how early on was that used? And so how important was your feature in making decisions, not just for one tree, but on average across all the trees? So the same way that we aggregated their votes, we aggregate the value that they used to split on. Questions on decision trees? Let me see what I'm missing here. Random forest. Oh, a key term here, ensemble. This is an ensemble, which means that you're combining together a bunch of different machine learning algorithms. So this is combining together a bunch of decision trees, in this case, to make an ensemble, which is this algorithm. In gradient boosted tree, a gradient boosted tree is very similar to a random forest, but instead of making these really deep trees, it makes something called weak learners, which are really short, stubby trees, which just 1 or 2 splits and then it cuts it off. And then whatever, it uses this algorithm to focus on, like, what did it get wrong? So if you're studying for a test, right, and maybe you take like a practice test, you don't take your practice test and then decide, well, I'm going to go study all that material again. You think, what did I get wrong? Well, I'm going to focus on that material and see if I get that right next time. So that's what gradient boosted trees do. Theoretically, we won't dive into that because we're out of time. But so gradient boosted trees focus on what did I get wrong and try to improve on those records. Okay, any thoughts? That was like way faster than I wanted it to be for random forest and all that junk, but I want to get to us creating a practice document. Any thoughts on this? Maybe I'll take a picture of this. I'll send some links, some videos that'll probably describe it 10 times better than I did. What do you guys think about this algorithm compared to linear regression? Easier to describe in an interview?
Uh-huh.
Oh, thanks, Siri. That was useful. Siri thought it was easier.
I think I would have to watch it like a couple other times so that I can
Definitely.
be able to describe it, but I think you can see a visual of the other two compared.
I have some great videos that I've really enjoyed watching here. I'm watching these on, and I'll send those to you. StatQuest, I think, is one of them. Is really good. I think they do a great job. There's a couple others too. I'll send those. Like this catchy little intro that always gets stuck in my head. StatQuest. Excuse me while I erase these. I don't want to do this again. While I do this, I'll just pull up the doc. You guys don't have to look at the eraser board. let's all huddle on this dock. And in here, if you guys shared the link, I'm going to ask you guys to fill this out. What do you think are some of the concepts? Let's see, I'll put some high level. We talked about linear regression. What do you think you should know about linear regression? What do you think you should know about modeling methodology? I guess there's kind of a topic here called like classification versus regression, and then there's supervised versus unsupervised, modeling methodology, and let's do decision trees, random forest. I think that's all I'll ask you about. I hope I covered most of the topics in there. All right, if you guys want to, it's a self-created study guide, if you want to call that, or topic, what did I call it? Exam topics. Okay, do that while I erase the word. Collaborative effort here. Put you guys on the spot.
Hey, Emily, I think we need edit access.
Oh, so sorry. Share. And with link can edit. Copy link, done. All right, ignore that previous link. Try this new link. Maybe it'll be the same, actually. Looks the same. Maybe you just need to refresh now. I don't know exactly how their provisioning works. Here we go.
Wow. Whoever's analyst got all the answers for questions.
And I know it's the result. This has to be ChatGPT.
There you go. Hey, you can use ChatGPT.
No,
That's valid.
someone's writing on this.
It's probably John.
That was a tad. Oh.
Only if you're logged in or you logged into Google.
Okay.
They didn't let me not log in.
I don't know.
Everybody's
Yeah.
There we go. Bias variance trade-off. I like it.
I don't know.
Let me see if there are other topics. Breeze through our material from the first
This
section.
is one thing.
Yeah, we won't have a ton of time. It's 20 questions. Oh, I know. You know what? I think I have another doc. probably also, in addition to linear regression, we also talked about KNN, K nearest neighbors.
Which one was the one that had? It was related to the payment, but.
Oh, K-means clustering. I won't ask about that because I always had it on the back of my mind to get back to, and I feel like we never really got back to walking through that algorithm. But I think that's what is that what you're thinking of? K-means clustering? Was it a clustering algorithm?
It was related to the y equals mx plus b. But I think I am thinking of KNN.
Okay. Yep. KNN, K nearest neighbors. Yep, clustered together based on distance. You can use like Euclidean distance or
Is the bias different?
is the what? Is the bias different? Yeah, the bias variance trade-off.
Oh,
That's a good one, by the way. I forgot about that. And then
overfitting.
overfitting, absolutely. You should put overfitting in there.
You won't let me edit. You won't let you edit?
Oh, try refreshing. See if it'll.
I'll just close them.
Definitely put overfitting. Oh, there we go. Somebody put that in there. What else is closely related to overfitting? Starts with a G. I say it a lot.
Generalization.
Yeah. Generalization, generalizability. Let me see what other things.
Generalization.
Say again.
Prediction.
Generalization, same thing. Yeah, same concept. Let's see.
Traditional programming.
That's a good question. I don't think I have any questions around like object-oriented programming versus scripting. I know we talked about that at the beginning, but I don't think I have any questions there on that. The process that you need to apply to your features to get them into, I guess a question might be like, what are features and what are, what's Y hat and that, but what am I looking for? Like we talked about one-hot encoding, and we talked about ordinal encoding and scaling. All of those are kind of like transformations.
If you did one on test split, would that be more of an example? And then would you ask us like, how would you input the code for it? Or would it be more like, which of these four codes would be
Good
right?
question. I won't ask you guys to do any coding.
Okay.
So they'll be all concept questions. They'll all be multiple choice. Yeah, I won't do any coding, and they're all going to be conceptual. I might have, look at this training set curve versus this test set curve, and when is the model overfit? That could be one. I'm scared that I'm scaring you guys. It should, if it's overly difficult, I'll curve it, so don't worry. And I'll curve it. And that's my fault if it's on me if, everybody just bombs, then I did something wrong. So that's good to know too. And
The B, what's the formula? That's what I was thinking of.
the B.
The B.
Oh, yeah. That's exactly right. Yeah, the intercept, the bias.
Yes.
Yeah.
Who's writing this? Thank you.
You're getting a lot of appreciation for what you're writing. Thank you. You got some thank yous.
It was anonymous grizzly.
Let's see. Honest Grizzly, I like it. I might ask like the difference between like fit and predict. We talked a lot about unseen data, why that's important. And then I might ask a few algorithm questions. Stuff about the decision tree, random forest, KNN, and linear regression and logistic regression. I think that's good. I don't think we're going to have any more room. I think that'll take all. That seems like 20, 25 questions. That's going to fill those up. But definitely modeling methodology. That might be an order question.
Would any of these, this might be a lame question, but
Yeah.
would any of these questions say like, which of this, like, you're importing, I don't know, nearest neighbor, which is the, like, is it pandas or is it sklearn?
Oh, no,
No,
I
okay.
don't do that to you. No, I don't even know that. I just Google it.
Okay. So
No idea. Yeah, no, I won't do that to
name
you.
one of the data sets thing we were utilizing.
No, I won't do that either.
Drawing the confusion matrix or something.
Parametric versus non-parametric models. Maybe I'll have you guys classify those. I also have no idea the format that I'm gonna have you guys do, like, I don't know, Survey Monkey. Oh, parametric versus non-parametric. What's the purpose of a grid search? By the way, I'm just saying these out loud and then hoping I remember to write these down later, so.
So you'll read the sheet.
Is that gonna be saved?
Yeah, it's already.
Yes, you should have this. I didn't see any of that. Yeah, I think that's a good. If I have any in here.
Did they close the space?
They closed the space. Oh, do space. I think they moved temporarily.
Getting like broken down or something.
Yeah.
The building moved.
They moved to like a school building, didn't they?
Or-
Yeah,
I
temporarily.
just know they moved somewhere.
Yeah.
For the time being, because they're gonna redo their building and then go back, right?
Yeah, then they're gonna go
Oh
back.
my god.
Yeah, so they're in this like,
It was, I was gonna say, it was not so long ago. Maybe like 3 years or something. Yeah. Waste our money.
North 90th. And the, Milton is a program. Which happens is it's very sketchy how they're being embedded into the library, because it's profit-based. It's considered a nonprofit through this like foundation, but once it goes into the library, lenders, it's a city. So you're not supposed to combine funds, but somehow we're embedded in it. That's just library. It's like super like.
interesting.
So they say like sketchy, and then they told me what foundation. I'm like, oh yeah, that is sketchy. These are the people that are in there. So.
If I give you a line with XY coordinates, you should be able to tell me like what's the B and what's the M. for like y equals mx plus b.
Without using ChatGPT.
I'll give you grid.
Okay, like using, okay, like in math.
Yeah,
with the-
remember
okay.
rise over run is your m. So, and then just remember how to calculate r squared as well is probably the other question I might throw in there. And I'll really try. I feel like maybe I won't even put all these in here, but it just seems like a lot. I'm gonna try to. I'll make this. I'll take it myself, and then if I'm taking more than like
Give it to your 1-year-old.
a minute a question, he'd eat it. Paper.
I would say find the
Again,
fifth
curved.
password.
So, also, I'm pretty sure you guys all turned in your homework. So, you're really, if you look at the way that 20 to 25, somewhere in there. If you look at the way that I structured this class, you can actually bomb the exam as long as you just did everything else and then you pass. So it's.
But you wouldn't know until after the next week.
Oh, good point. Good point. Yeah, I did that part poorly. Okay, we're at 9:02. If you guys do have questions, just ping me questions. Help each other out. Maybe fill some of this stuff out. And then we'll see you Wednesday. And we can start Wednesday with any questions that you guys have. And okay.
Great, thank you.
Thank you guys. We'll see you Wednesday.
Thank you.
See ya.